Hey everyone, welcome back to another deep dive. Today we're going to tackle something that blew my mind in BIO259 today.
Oh, yeah, Dr. Rosario's lecture on muscle activation.
You know it. I thought I had a handle on how our brains tell our muscles to move.
Seriously, same here.
Mm.
But the way he explained the whole electrical signal to chemical messenger thing, whoa.
Right, it's way more complex than I ever imagined.
Totally.
Dr. Rosario, maybe you can help us break this down. You mentioned in class that our brains and muscles speak different languages, so to speak.
Yeah, the major ways that signals are passed are either through chemical signals or through electrical signals. So most of what we've seen in this class up until this point has pretty much been chemical signaling. This is when chemicals like acetylcholine or calcium are released, they travel to their destination, and they're finally caught by a receptor. So keep in mind that this is a very short-range form of communication. We also really need a long-range form of communication to get signals up and down our body. For those, we have to use electrical signals.
Fast, efficient, perfect for sending messages long distances.
Right, those rapid bursts of electricity zipping along our neurons.
Exactly. But muscle fibers, they're a different story. They need a chemical signal to kick into gear.
Right, remember, that's the calcium that needs to bind to the troponin.
Okay, so how do we bridge that gap? How does an electrical signal become a chemical one?
That's where the neuromuscular junction comes in. Think of it as a tiny meeting point between a neuron and a muscle fiber.
Where the nervous system meets the muscular system.
So walk us through what happens there. You described it in class as this incredible chain reaction.
So let's start with the electrical signal that travels down the neuron. That electric signal, which is called an action potential, by the way, makes its way all the way down to the axon terminal.
And that triggers the release of these chemical messengers. We call them neurotransmitters.
And the star of the show, if I remember correctly, is acetylcholine, right?
You got it. Acetylcholine floods the tiny gap between the neuron and the muscle fiber.
Yeah, so we usually abbreviate this as ACH, right? Acetylcholine, ACH. But yeah, this small chemical is released from the neuron onto the surface of the muscle. And what do we have on the surface of the muscle? The sarcolemma receptors. And they're just like sitting around waiting for ACH. Once the ACH binds with the sarcolemma receptor, a secondary electrical signal is generated right on the surface of the muscle.
Okay, so we go from electrical to chemical, then back to electrical again. All the back and forth. Why not stick with electrical the whole way?
It's all about efficiency and specificity. Electrical signals are great for long distances, but to trigger specific actions within a cell, like muscle contraction, you need a more targeted approach. That's where chemical signaling shines. But how does that electrical signal on the muscle surface actually cause a contraction? I know we keep mentioning this cross-bridge cycle, but I'm still a bit fuzzy on the details.
Well, the key is calcium. Calcium is like the fuel that powers muscle contraction.
Right. We know calcium is important, but that electrical signal can't just zap the calcium stores directly, can it?
Nope. This is where things get really cool. Enter the T-tubules. These are like microscopic tunnels that run deep inside the muscle fiber. They carry that electrical signal right to the muscle's calcium vault, the sarcoplasmic reticulum.
So these T-tubules are like a direct pipeline from the surface to those calcium reserves.
Exactly. They make sure the message gets delivered loud and clear. The signal travels down those T-tubules and boom, the sarcoplasmic reticulum releases its calcium ions.
Yeah, and remember, those calcium ions, those are the chemical signals that determine whether or not cross bridges are made. Without calcium, you have huge molecules like tropomyosin blocking access between the thick and thin filament, but when the calcium binds, cross bridges are able to be formed.
That's wild. So much happening at such a tiny scale. It's making me appreciate the simple act of moving my fingers in a whole new way.
Me too. It's like this whole hidden world of activity going on beneath the surface.
And we've only just begun to explore it. We haven't even talked about how our bodies control the strength of those contractions. That's where the concept of motor units comes in.
Ooh, yes. Motor units. You had this cool analogy with light bulbs and light switches, right?
Exactly. A motor unit is like a single light switch controlling a set of bulbs.
One switch, multiple points of illumination, but instead of light, we're talking muscle power.
Exactly. And just like you can have different size light bulbs, you can have different size motor units. Some control just a few muscle fibers, while others control hundreds, even thousands.
So why does the size matter? Why have different sized motor units?
Well, think about it. If you just want to dim the lights in a room, you don't need every single bulb blazing, right? You just turn on a few.
So it's like our bodies are being efficient, only using the muscle power we need for a given task.
You got it. Sometimes a gentle contraction is enough. No need to fire up all the muscle fibers.
Okay, I see where you're going with this. But how do our bodies know which motor units to activate? Is it random?
Not at all. There is a very specific order to how we recruit motor units, and it's called the size principle. We start with the smallest, weakest motor units and gradually add larger, stronger ones as more force is needed.
So it's like gradually increasing the brightness in a room. Start with a few dim bulbs and keep adding brighter ones until you reach the desired level of illumination.
Exactly. It allows for these smooth, graded increases in muscle force, which is pretty darn important if you think about it.
It really is. I never realized how much strategy goes into something as simple as muscle contraction.
It's a fascinating system, and we've only scratched the surface.
So last time we were talking about motor units, right? And how our bodies use them to fine-tune how much force a muscle generates.
Right? Like having a dimmer switch for your muscles.
Yeah.
You only use the amount of light bulbs, aka muscle fibers, that you actually need for the job.
Exactly. But there's another layer of control that we need to add to this, and that's frequency.
Frequency.
Yeah, remember Dr. Rosario was talking about this in the end of class. It's not just about which motor units get activated, but how often they get those signals to fire.
So it's not just an on-off switch. It's more like how quickly we're flipping that switch on and off.
That's a great way to think about it. Imagine you're tapping a drum. A single tap makes a quick sound. But if you start tapping really fast, those individual sounds start to blend together.
And you get a louder, more sustained sound.
Holy cow, that is a great analogy. So let's think about what happens when you start tapping really fast, right? Individual vibrations add together over time to make a larger, fuller, more sustained sound. That is exactly the principle of temporal summation in action.
Right. The same thing happens with muscles. If those signals come in rapid fire, the muscle stays contracted. It doesn't have time to relax between those individual twitches.
So instead of one quick twitch, you get this nice, smooth, continuous contraction.
Which makes a lot of sense because, in real life, we rarely just use our muscles for a single quick twitch. We need them to hold positions, lift things, move smoothly.
Totally.
But Dr. Rosario, what if we just keep increasing the frequency? Is there a limit to how much force a muscle can produce?
For sure. All right, so the role of calcium doesn't change here. It is the chemical signal that allows cross bridges to form, right? So the only thing that you need to keep in mind is that each time an electric signal is fired down a motor neuron, eventually it'll just cause the sarcoplasmic reticulum to release a little bit of calcium.
That's right. Now, remember how we were talking about the size principle, how it determines which motor units are activated? Well, frequency gives us another layer of control on top of that.
So not only can we recruit more motor units as we need them, but we can also tweak how fast each of those motor units is firing to fine-tune the force even more.
Precisely. It's like having multiple volume knobs on a soundboard. You can adjust the overall volume by recruiting more units and then fine-tune the sound of each instrument by changing their individual frequencies.
Our bodies are way more sophisticated than I ever realized. This has been an incredible deep dive, Dr. Rosario. Thank you so much for walking us through all this. We've learned so much.
Seriously, we went from those tiny little neuromuscular junctions to the big picture of how our muscles generate force, adapt to different tasks, and even protect themselves from damage.
It's mind-blowing. So to all our listeners out there, thanks for joining us. We'll see you next time, ready to dive into another fascinating topic. And in the meantime, keep those muscles working, but don't forget to give them a rest when they need it.